Hello everyone, my name is Yun Chen. I'm glad to be here to share my research work with all of you. Today, I'd like to talk about a molecular dynamics study of nostrils with various silicon to alumina ratios. If you are not familiar with molecular dynamics simulation, I will walk you through it from the following three parts. First of all, we need to know what is simulated. It can tell you the movements of atoms. That means you can predict the trajectory of all the atoms as a function of time. As for how does it work? Well, it's not that simple, but basically you play with Newton's equation of motion. I guess the most interesting part you want to know is why do you want to perform molecular dynamics simulation? Well, the advantage of it is that it allows us to explain macroscopic behavior from ensembles of microscopic entities. We can obtain many useful information, as you can see here. Another thing, my research object is nostrils. We all know nostril is the main reaction product of geopolymers. When we describe nostrils, we always hear some familiar phrases like three-dimensional cross-linked structure, linked by silicon and alumina tetrahedrons, right? Actually, people already do their best to study nostril with all available experimental techniques. So, if we want to further study nostrils, we need to look for simulation results, simulation techniques. So that's why I carried out molecular dynamics simulation to study nostril structure. I have to say there are already some researches studying nostrils by molecular dynamics simulation. However, the way we carried out simulation is different. Here you can see, to build the initial structure, three types of precursors: silicate monomers, aluminate monomers, and sodium hydroxide were put randomly into a simulation box. Silicate to alumina ratio ranges from 1 to 4, while sodium to alumina ratio is fixed at 1. Force field is another input you need to have to describe the potential energy among all the atoms. After that, you can perform molecular dynamics simulation. At the end, the system becomes stable. You will have the final structure. We can see the final configuration is completely different with the initial structure. So something must be happened during this process. Let's have a look. We can calculate Q1 at different simulation time to see the reaction process. Figure 1 is the evolution of silicon side with simulation time, and figure 2 is alumina side. We can see at the beginning, 100% Q0 is Q0 because all of them are monomers. As time went on, Q0 decreased and Q1 emerged first, followed by Q2, Q3, and Q4. This is consistent with the reality. Alumina side also has the similar trend. The only difference is that for alumina, we have Q5 and Q6. However, we can't tell whether these Q5 and Q6 are from nostril or not. The only thing for sure is that they do exist at the system. So we need to look at the final system. The left figure is the final system. We can see it contains several phases. In the middle is the biggest cluster, which is our desired nostril. Around it, we have some individual oligomers and many water molecules. All of them are simulated reaction products, which is also consistent with the reality. After that, we need to take out nostril from the whole system to further study its structural information. First of all, let's look at bond length. We can see the bond length for silicon oxygen and alumina oxygen they are all consistent with the other research. The only thing I want to put it up here is that for higher silicon to aluminum ratio, we have a longer bond length. Besides bond length, bond angle is another important parameter. Here is the silicon-oxygen bond angle. We can see it mainly located at 110 degrees. This is because all silicon exists as tetrahedron. So in a tetrahedron, we can see the angle is exactly at 110 degrees. For alumina, oxygen bond angle, we can see has a much wider range. That means not all alumina exists as tetrahedron. If you remember, we have Q5. So Q5 means alumina is bonded with 5 atoms. So in this case, we can have small angle like 80 degrees, and we can also have large angle goes up to like 150 degrees. Besides these two bond angle, actually we have another type, TOT bond angle. From all nostril we simulated, we have silicon-oxygen bond angle at a maximum of 20%. Most of them are silicon-oxygen alumina bond angle. And it's interesting to find a small amount of alumina-oxygen-alumina bond angle, which is against the Lowenstein's rule. So that means the Lowenstein's rule is not always obeyed. Now we come to SRD results. SRD results determine whether the structure we formed is nostril or not. Luckily, a typical hump for nostril can be found for all cases. An interesting point is that we can observe the hump shifts to smaller angle as silicon to aluminum ratio increases. This can also be found in experimental results. In this research, they believe the shift is because of different reaction degree, but I do believe the shift indicates something else. The hump shift to small angle means that the structure has larger interplanar spacing, which means the structure with a higher silicon to aluminum ratio, it has a less compact structure. Besides SRD, we can also calculate QN distribution, which is linked with NMR results. First of all, let's look at silicon distribution. From figure 8, we can see for lower silicon to aluminum ratio, we have more Q3 and Q4. That means the structure with lower silicon to aluminum ratio, it has a more cross-linked structure, which is consistent with our reality. However, according to literature, we all know that silicon in nostril mainly exists as Q4, and Q1 is supposed to be only occupied a very small amount. It seems my simulation has more Q1 and Q2 compared with the experiment. Actually, this is because of surface effect. If you remember, my simulation took place in a very small box. As a result, the structure I obtained has a large surface. That's why I have more Q1 and Q2. But if we compare silicon-4 distribution, we can see my simulation result is actually quite consistent with other experimental results. And another thing is that we can see silicon-4 tends to link it with 4 alumina atoms. Even though the silicon to aluminum ratio goes to the highest, this one, it also tends to link at least 3 alumina atoms. Here is the alumina site distribution. We can see most of them are Q4 and Q5. Q4 is not surprising, but Q5 may be beyond your expectation. We used to believe that pentacoordinate alumina and 6-coordinating alumina only come from unreacted raw material in geopolymer paste. Until recently, Walkley proposed a new model for nice gel which contains 6-coordinated alumina. According to the literature, both pentacoordinate aluminum and 6-coordinated alumina are considered as charge balancing low, just like sodium ions. By now, both simulation result and experimental result show us that not all alumina in nice gel is tetrahedral. Okay, in short, in this work, I performed molecular dynamics simulation to study nice gels. During the simulation, the system went through a polymerization process similar to reality. At the end, we obtained a nice gels model, and we also have some interesting results like the existence of alumina-oxygen alumina bond angle and pentacoordinate alumina. We also studied the effect of different silicon to alumina ratios on the structure of nice gel. This information can help us to explain their mechanical properties. Actually, I don't have time to show you my results about mechanical properties. I hope I have the chance to see many of you next time. At the end, I'd like to say thank you, and I hope you enjoyed the conference.